is Eric Coleman. I'm a first-year PhD at the University of Pisa, and I'm going to be giving a short talk on in-context interference in chat-based large language models. This was done mostly because of the recent popularity with large language models, and users tend to typically interact with these models in small sessions or contexts. So we assume that these interactions occur in closed environments, assuming the models have no internet access. So they interact with these models without having to, they don't have direct access to these models. So the only way to introduce new knowledge into these models is through the current context via prompts. So you introduce new knowledge into the model with the use of hard prompts. And this is what we call in-context learning. Users expect the model to have perfect memory when it comes to the session they are working in. So you introduce new knowledge via your prompt and you expect the model to understand or perfectly remember what you entered. But that's not the case because some models performance tend to decrease along the line as the context gets bigger. So that's what we were trying to discover and understand with this experiments or these sets of experiments we conducted. So how do we evaluate this these events? So we want to evaluate the current session, how the model behaves within the session when new knowledge is introduced. So how do we do that? So the basic idea was to introduce a set of facts or stories within the current session. So the model's performance is assessed as more information is introduced. So we start with an initial input, that's the first story, and each story has a corresponding question. So at each step, so with each input, a new story is given with associated questions. So we expect that the model is able to, typically you expect the model is able to remain consistent with the information added. So remember the facts introduced and be able to answer the questions, even if the question is asked, the story is introduced at the beginning, you ask the questions at the end of the context, it should be able to follow. But that's not the case. So with this experiment, we introduced a new benchmark based on the Babi datasets. So the Babi dataset is used to typically evaluate how the retention and reasoning capabilities of language models. And with this, what we did was we simplified the datasets because firstly, we want to know if the model is able to understand these questions even without prior knowledge. So like you introduce a very simple set of facts and you ask questions and see if the model can answer it anyway. So the two things we did, simplify it by firstly replacing the entity names. So in the original data sets, you have repetitive entity names. So each story has the same set of entities. So what we did was we replaced these repetitive entity names with unique ones to make it easier for the model. And then further simplification, we reduced the size of the stories and asked only 2 questions. So in the first experiment where we had one context, one story. So we used a Vicuña model, Vicuña 13B, which is a relatively small model, and it's open source. It was running on a single GPU. And we introduced these stories via prompts. So with the adding single stories within a single context, this is to test, to have a baseline, so know if the model is able to answer these questions anyway. So the simplest story. So we ask a question based on the story we provided, and we reset the context. So with this, the accuracy was very high, 100% with the short stories. And then we introduce full stories, where with the full stories, it's a bit more complex. and slightly more reasoning is required by the model. And with that, the accuracy wasn't as high as the short stories, but it was around 58%. So with this initial stories, we know the model can answer the simple questions when in a single context. But what happens when we decide to introduce these facts continually within a single context? So with this, we have one context, and we continuously add different stories with different questions, and the performance it starts well, but as it goes on, the performance tends to degrade. Mostly, the more tokens we consume within the current session, the more the performance goes down. So starting with this experiment, the maximum number of tokens were 2,048, and the average token consumption per story. So with the full stories is 67, and with the short stories is 19. So we want to know how the model performs as we continuously increase the size of the context. So this graph mostly shows the accuracy with the introduction of new stories. So when we use the short stories, we have a longer context because it consumes less tokens, and the performance is not the best, but it degrades over time. But with the full stories, which consumes more tokens than the short stories, the performance isn't high in the beginning, and it also degrades really fast. So with the model we had, using the full stories, we can only have a context with about 5 stories, but with the short stories, you can have 8 or 9 to 10. So this just shows that. And the thing we wanted to see, can we somehow alleviate this interference within the model? Can we somehow have a longer context whilst having good performance without having direct access to the model? So what we came up with were two simple solutions. So the first solution was to summarize the entire context you're working with, and use the context, the summary as part of the prompt. So every time you introduce new knowledge via the prompts, it's combined with the entire context, and it's summarized, and the model has to answer the question from this summary. And what we notice is we can have a longer context in this way because we consume less tokens than having to incrementally add to the current context. And the other solution was removing old stories. So within the context you're working with, every time you add a new prompt, you remove one of the old prompts from the start. So you add story 10, you remove story 1. You add story 11, you remove story 2. So with this, you have a fixed context size. So you can define a fixed context size of, say, about 10 stories. And with this fixed context size, you consume about a fixed number of tokens. And the performance is not as bad as previously. You're able to somehow maintain some level of sanity within the model whilst having a longer context, if I should say. This experiment, the results are mostly based on the type of model we use because it's a much smaller model, and it has a smaller fixed number of tokens, not like the larger ones we have today. But this interference, it's also based on the model. Different models are more robust to this interference in different ways. So, but we know that this can be somehow fixed by doing certain things like summarizing the current context or removing some stories if you can, to have a longer context whilst having the model perform at its best. So thank you. If you have any questions.
Great. Thank you for that great presentation. I believe that we can leave the question for the end of the session. However, if you want, you can answer a few questions offline in the Q&A section.
Okay.
So now we can pass to the next presentation. So I don't know, Seren Gok Dirim, I don't know if you're there, and I'm not sure if I pronounced your name correctly. So sorry about that.
No problem at all. It was okay. I'm here. If it's my turn, I can
Yes.
present.
Yes, please share your screen.
Okay, I will share my screen. Can you see it?
Yes, perfect. You have 15 minutes.
Yeah, I am also trying to open up my camera, turn on my camera. Oh. Sorry.
Okay?
Yes.
Okay, perfect.
Hello, I am Ceren. I'm a PhD student. Sorry. I'm a PhD student in Eindhoven University of Technology. I'm working in automated machine learning group. Today, I would like to present our work called adaptive continual learning. Before introducing our approach, I would like to briefly provide an overview of the fundamental terms related to continual learning. Continual learning aligns with the way how humans learn throughout their lives, building on prior knowledge while acquiring new skills and adapting to new information. And similar to how we might forget details of a subject we haven't revisited in a while in continual learning, models may struggle to remember the earlier learned tasks when focusing on the new ones. Extensive research has been conducted, and still there is a large ongoing effort to address the challenge of catastrophic forgetting. The solutions are primarily classified into three categories as regularization-based, memory-based, and architecture-based. Like how our brains consolidate essential information, regularization helps the model focus on critical parameters for each task. And memory-based methods relates to how we recall about past experiences to reinforce our memories. And finally, architecture-based methods analogous to how the human brain's architecture evolves and adapts as we learn new skills. The AI model can modify its architecture dynamically. Commonly utilized approaches, particularly those involving regularization and memory, often make a crucial but limiting assumption, which is assuming that each task will require the same set of hyperparameter values. For example, fixed learning rates are commonly used in training models. This assumption implies that the learning rate is predetermined and does not adapt to the evolving data distributions or changing the complexity of tasks. A constant learning rate might not be optimal for learning new tasks with differing complexities. Even though we have techniques like learning rate schedulers, the starting learning rate at the beginning of each task is usually the same, and the specific points where we might adjust it are also set uniformly for all tasks. So in a way, it's still like saying it's fixed throughout. Similarly, traditional regularization-based methods often assume fixed values for the regularization hyperparameter across all tasks. This assumption implies that the regularization strength chosen during model training remains constant and optimal for all subsequent tasks. And many memory-based approaches assume a predefined memory size per task. This implies that a fixed number of samples or experiences from a task are stored for future reference. While it's possible to scale the memory size with the number of tasks, it's important to note that this approach isn't entirely adaptive either. Even when scaling, we end up with defining a fixed total memory size, which might not effectively adapt to the varying demands of each task. The fixed assumption of hyperparameters brings important limitations. The limitations of fixed hyperparameter setting in continual learning can be outlined as, first, lack of adaptability. A fixed hyperparameter setting might be suitable for one task, but suboptimal for another. I would like to go over with the fun example to emphasize these limitations. Imagine having a one-size-fits-all recipe for cooking. While it might work for certain dishes, it would likely be inadequate for others. Fixed hyperparameters operate in a similar manner. They assume the same recipe fits all dishes. However, just as you wouldn't use the same seasonings for both a dessert and a main course, fixed hyperparameters struggle to adapt to the varying complexities of different tasks and memories. Second, risk of overfitting or underfitting. Fixed hyperparameters may lead to overfitting or underfitting, especially when the data characteristics change. Think of a fixed hyperparameters like using a single cooking time for all recipes. What if the time was meant for baking cookies, but you are making a pasta dish? The result won't be ideal. Similarly, when we apply the same hyperparameters or cooking time to new tasks, we risk overbaking or undercooking our model, leading to suboptimal outcomes. And finally, possible inefficiency in resource usage. Consider using the same quantity of ingredients for all dishes regardless of the recipe. This approach would likely lead to wasted ingredients and unsatisfactory meals. Fixed hyperparameters similarly ignore the recipe or specific needs of each task, resulting in inefficient usage of computational resources or, for example, memory sizes. The limitations of a fixed hyperparameter setup in continual learning prompt the need for a dynamic and adaptive approach. We present ADA-CL, a concept designed to mitigate these limitations and bolster model performance in evolving continual learning scenarios. With this way, we aim to overcome the rigidity of fixed hyperparameters, enhance adaptability to diverse and evolving tasks, and optimize the model performance by dynamically adjusting key hyperparameters based on task characteristics. ADA-CL defines the regularization magnitude, learning rate, or memory size per task as functions that consist set of incremental tasks, conditioned on the current learning task and all previous tasks. In a formal context, we express eta t as a sequence of learning rates, eta 1, eta 2, up to eta t. And similarly, lambda t as a sequence of regularization strengths, lambda 1 up to lambda t. And additionally, mt represents a sequence of memory sizes, m1, m2, and up to mt. The values for eta t, lambda t, and mt are determined through an optimization process that minimizes the given objective. Here, VT is a randomly selected, class-balanced validation subset of the current task and previous tasks that guide the model's adaptation with careful consideration of both new and previous task characteristics and prevent bias over certain classes. After each round of model training, we utilize the validation set VT to evaluate the chosen hyperparameter configurations. This evaluation process is vital in determining the most effective hyperparameter settings and ultimately aiding in the optimization process. After the overview of ADA-CL, I would like to briefly mention our experimental setup, then conclude my presentation. We will be substantiating our approach through evaluation using split cipher 100 and mini-ImageNet dataset, each organized into 10 tasks, each comprising 10 classes per task. We carefully selected 4 foundational baseline methods to serve as strong references for our adaptive approach. 2 of these methods, elastic weight consolidation and learning without forgetting, operate on a regularization basis, while the other 2 methods, iCarl and weight alignment, fall under the memory-based approach. First method, EWC, aims to retain crucial weights from previous tasks by penalizing deviations in weight values. On the other hand, in the LWF, the knowledge is distilled from the old model to guide the training of the new model, ensuring it retains important information while adapting to new tasks or data. iCarl leverages stored exemplars from past tasks to mitigate catastrophic forgetting and improve task-specific learning. And weight alignment is a classifier correction method that adjusts the weights of neural network, specifically focusing on the classifier layer. Its aim is to prevent bias or imbalance in the classifier by appropriately aligning the weights, ensuring fair and accurate predictions across different classes or tasks. These chosen baselines are intentionally complementary, covering different aspects of continual learning methods. By implementing our adaptive approach to these strong foundational methods and comparing against their original version, we aim to showcase the effectiveness and versatility of our proposed approach. To find the best hyperparameters, we employ a powerful search algorithm known as 3% estimators. TPE, a method rooted in Bayesian optimization. It's an important part of our hyperparameter optimization process. In our study, TPE serves as a search algorithm. It navigates within specified ranges for crucial hyperparameters such as learning rate, regularization strength, and memory size per task. This exploration is aimed at finding the best values for those hyperparameters. We evaluate the chosen configuration within the defined search space of hyperparameters using the validation set. This allows us to assess how well the model performs with those specific settings and aiding us in finding the most effective hyperparameter settings. Lastly, we will comprehensively assess the outcomes using widely recognized and commonly employed metrics, notably incremental accuracy and backward transfer. These metrics provide a robust evaluation of the model's performance in the context of continual learning and knowledge retention. To summarize our work, we raise the important issue of adaptive hyperparameter selection in class incremental learning. We propose to predict the learning rate, regularization magnitude, and memory size conditioned on the state of the deep learner and the current learning task via Bayesian optimization. And finally, we aim to demonstrate the efficacy of adaptive learning through experiments on well-established benchmarks and showcasing substantial enhancements in accuracy while minimizing forgetting. We believe with this study, we will lead the way in introducing the concept of adaptive hyperparameter optimization in the realm of class incremental learning. And as the field advances, we anticipate that these insights will shape the evolution of advanced continual learning approaches and empower deep neural networks to adapt to evolving tasks. Thank you for listening.
Thank you for that amazing presentation. So if anyone have any question, please use the Q&A section. So now what we can prepare for the next presentation. Federico?
Yes, I'm here.
Perfect. So thanks, Seren.
Okay, thank you.
Okay.
And I will ask all the presenters if they can stay at the end. So if any attendee want to ask like question by raising their hands, and then maybe we have time a little at the end so they can answer. Like,
yes, of course.
so great, thanks Federico. Now is your time.
Okay. Hello, everyone. I'm Federico Giannini, a PhD student from Politecnico di Milano in Italy. I'm glad to be here. And my talk of today will cover the challenges of learning in dynamic environments and how to address them. I will start the presentation by introducing the challenges of learning in dynamic environments. Then we will see together the behavior of stochastic gradient descent when applied to data stream. At this point, I will introduce progressive neural networks that will be the starting point of our solution, that is continuous progressive neural networks. Then I will present the experimental campaign, and finally, I will explain what we are working on now in order to address more challenges in the context of learning in dynamic environments. When we learn from a data stream, we must face four main challenges. Firstly, we want to learn continuously from single data points or mini batches. Therefore, we cannot apply the classical machine learning approach that assumes that the knowledge is entirely represented by a bounded data set. Instead, we want to continuously make prediction and learn each time a new data point or a new mini batch is generated from an unbounded data stream. Then data can change its distribution, and this problem is known as concept drift. Our goal is to quickly adapt to new concepts in order to not lose their performance. Next, as we highlighted in our previous work towards evolving analytics, data can show temporal dependencies, and usually a data stream can be seen as a time series in which the data point at time t could depend on the previous data points. To take this situation, we should consider sequences of data points rather than single data points. Finally, when we learn a new concept, we may forget the previous one. And this problem is known as catastrophic forgetting. The goal is to achieve a trade-off between the ability of learning new knowledge, that is plasticity, and the ability of remembering the past one, that is stability. These problems are addressed partly in literature. In fact, the stream machine learning area focuses on learning continuously from single data points and on managing and detecting concept drifts. But it usually assumes the data points within a concept to be independent, and therefore it fails to account for temporal dependencies, and it usually ignores the problem of catastrophic forgetting. On the other side, continual learning focuses on avoiding catastrophic forgetting in deep learning models and managing concept drift. But it usually assumes each task to be represented by a large batch of data called experience, and it does not delve into the problem of temporal dependencies. Finally, time series analytics is meant to deal with temporal dependencies, but it's poorly applied to data streams. For these reasons, I will present a solution to jointly deal with all of these four challenges. If we want to learn continuously from a data stream, we could apply the stochastic gradient descent, since it's an incremental algorithm. The problem arises in the case of concept drift. If the new concept introduces a new classification problem that is totally different with respect to the previous, the minimum of the new loss function could be far away from the previous. And therefore, the stochastic gradient descent may require more steps to reach the new minimum. In this case, the adaptation to the new concept would be slow. When we reach the minimum of the new loss function, the more the new classification problem is different with respect to the previous, the more we will forget the previous concept. To take the situation, we could apply the continual learning strategies, and therefore we choose the progressive neural networks strategy, that is an architectural strategy to avoid catastrophic forgetting and leverage transfer learning. The architecture starts with a single neural network that is called column, and then when a new task or a new concept arises, it adds a new column to the architecture. Each hidden layer of this new column receives the output of the previous hidden layer of the same column, and the outputs of the previously the layers of all the previous columns. This way, progressive neural network can reuse the previous knowledge and can combine it to the knowledge acquired directly from the current task. Moreover, it can avoid the catastrophic forgetting by freezing the weights of the previous columns. Gate incremental memory, or GIM, builds a recurrent version of progressive neural networks to apply them on LSTM and to tame temporal dependencies. In this case, for each item of a given sequence, it applies an LSTM to the concatenation between the features representing the item and the output associated with that item of the previous column. But as I said, continual learning strategies are not meant to learn continuously from data streams. For this reason, we propose a new version of progressive neural network that is continuous progressive neural networks. Firstly, we want to learn continuously while taming temporal dependencies. To do so, we accumulate data points in fixed size mini batches. When the mini batch is full, we can apply a sliding window to build the sequences. These sequences will represent the input of an LSTM that we will call CLSTM or continuous LSTM. This way, we are producing a periodic classifier that requires a mini batch of data points to perform both inference and training. But this periodic classifier can consider both past and future temporal dependencies within a mini batch. Once we can learn continuously and we can tame temporal dependencies, we must deal with the other two challenges that are concept drift and catastrophic forgetting. To do so, we apply the GIM logic on top of CLSTM. In this way, we can use the transfer learning to quickly adapt to new concepts, and we avoid catastrophic forgetting by freezing the weights of the previous columns. The entire code that implements continuous progressive neural network is public and documented. You can find it on GitHub by scanning this QR code, and we presented this work at the Pacific Asia Conference on Knowledge Discovery and Data Mining in May 2023. Now we want to test our CPNN model, and therefore we run a complete experimental campaign on both generated and real data streams. We use two boundary functions alternated. Each boundary function produces two classification functions. One inverts the labels of the other. We combine these four classification functions to produce three abrupt concept drifts. Some drifts are called severe in the sense that they change the 65% of the label with respect to the previous concept. The other are called mild. Firstly, we want to investigate the needs of the different components of CPNN. We therefore run an ablation study in which we compare CPNN with the two ablated versions. The first does not manage concept drift, and therefore it results in being simply a CLSTM without the GIM logic on top. And this is the blue line. The other does not use transfer learning, and this is the orange line. And therefore it results in being simply a CPNN in which the columns are not connected. We can see in this plot the Cohen's kappa trend on different batches of a weather data stream, so it is a real data stream. We can see that CPNN adapts quicker to drifts thanks to the usage of the old knowledge. In this case, we are evaluating the Cohen's kappa with the frequential evaluation, in which each time we have a new batch, we first make prediction on it, test the prediction, and then we train. When the drift is severe, the version that does not manage drifts struggles. This is because a severe drift introduces a new classification problem that is totally different with respect to the previous, and therefore stochastic gradient descent may require more steps to reach the new optimum of the new loss function. Finally, we can see that the version that does not use transfer learning is quite always the worst, that is the orange line. Now we want to compare CPNN with the streaming machine learning models. We compare CPNN with different streaming machine learning models, but we are only showing the best streaming machine learning model that is adaptive random forest with temporal augmentation. To do so, we must adapt CPNN to make prediction on single data points. In fact, as I said before, CPNN is a periodic classifier that requires many batches of data points to make prediction. To do so, we make prediction on the first sequence of each data point. And therefore, in this case, the training and inference objectives are not aligned, since the training loss deals with many batches of data points. We can see that from the results, CPNN requires half concept to learn the first boundary function that is associated with the first and the third task. Then it usually outperforms SML models, and you can see that from the half of the first task onwards and on the entire third task, CPNN can outperform the stream machine learning models. On the second boundary function that is associated with the second and the third task, CPNN requires the entire second task to learn the boundary function, and then on the third task, it performs equally to the stream machine learning model. With CPNN, we deal with the four main challenges of learning in dynamic environments that are learning continuously, concept drift, temporal dependencies, and catastrophic forgetting. But new challenges arise with this work, and the first is to optimize CPNN for the anytime classifier scenario. In fact, as I said, the CPNN now is a periodic classifier. Therefore, we are working on a new version of CPNN that optimizes the prediction in order to make prediction on single data points. And therefore, we consider also during the training phase the first sequence in which a data point appears that will be the sequence in which the data point is the last item. Then, in a streaming world, the required amount of memory could be crucial. And therefore, we are working to reduce the required amount of memory by applying quantization to the old columns of CPNN. The reduction of the memory open to the application of continuous progressive neural network in a federated learning scenario, in which we usually have different quantized CPNN local models that learn from different parts of a data stream, and then at some point, we want to aggregate them and to build a federated model that will continue the training on the remaining part of the data stream. Finally, we only used progressive neural networks, but we could apply also other continual learning architectural strategies like piggyback and supermax in superposition. Before doing so, we must adapt them to be applied on recurrent neural networks like LSTM or GRU. And therefore, now we are working on the application on data streams of these other continual learning architectural strategies, and we are producing continuous version of them. That's all. Thank you for your attention. And if you have any question, I'm glad to ask.
Thank you, Federico, for that great presentation. So we will ask now Sarah if she can present. And of course, the Q&A is always open, so you can ask things there. And of course, at the end, we will try to have an open mic Q&A section. So I will ask all the presenters if they can stay a little bit after. So Sarah, if you can.
Hello, everybody. Can you hear me well?
Yes. Yes, I can.
Okay, thank you. So it's really an honor for me to show my work to a continual learning community. I am a PhD student enrolled in CISA in Trieste in the Department of Data Science. I will present my work about direct feedback alignment applied to continual learning. My supervisor is Sebastian Gold, and Biplov Arora is also helping me out. Okay. So what is direct feedback alignment? I think most of you never heard this about this. It's an optimization algorithm alternative for backpropagation. The main idea is that it works in two phases. In the first phase, there is an alignment phase. Also, in the name direct feedback alignment, it's present this feature. So in the alignment phase, even if the method starts from a different initialization points, the weights move towards all the same direction. So there is an implicit bias in this algorithm. And we already know that in continual learning, an explicit bias introduced to the loss, like for example in elastic weight consolidation, has been shown to be successful in continual learning. So we were wondering if this algorithm that has the bias intrinsically in the update rule could be helpful. So why is this alignment happening? So on the left, we see, for example, a representation of a 3-layer neural network with BP. We see that the forward pass goes through the feedback, the weight matrices. Instead, the backward pass goes through the weight matrices transposed. In DFA, the error is mapped directly to each layer, and the derivative of the following layers is not considered in the update rule of the early layers. Here, don't be scared. I just want to compare the equations of BP and DFA. The last layer is updated exactly in the same way. The error is mapped in the same way. In W2, the matrix of the intermediate layer has this difference instead. Instead of W3 transposed, we have B2. So it's intuitive to think, to understand that the weights of the last layer will have to align to the W3 transposed to really have the gradient. So in order to be able to update the loss according to the learning that it needs. For the update of the first layer instead, B1 is a proxy of W2 transposed and the derivative of the following layer. So B1, the weights of this layer will need to align to a bit of a more complex object, but still defined and depending only on the feedback matrix. The feedback matrix is initialized as a uniform random distribution and is kept fixed along through all the training. We can see later that we can change this feedback matrix for the different tasks in continual learning, or we can keep it in the fixed as well. Here is another representation of the alignment, and here they say memorize, but it's actually meaning learning the data set. So from an initial point of view, first the weight will align to the values of a feedback vector. Then among all the possible solutions of the weights, the solution that is selected is the one with the same gradient as the feedback vector. For example, here it's a small example. We have two positive numbers and one negative in the middle. So the solution that will be selected will be the one that has the weights with the same gradient of the feedback matrix. I hope this is clear. So what are the advantages of DFA? We already mentioned the implicit bias. We will try to exploit this bias for continual learning. The fact that the weights are not the same for the backward and the forward pass makes this algorithm more biologically plausible. In fact, was born in 2016 as a biologically plausible algorithm. And the train of the different layers can now happen in parallel, which goes in the direction of a saving of energy, which a continual learning method should keep always into account. And then has other technical advantages. For example, the activation function can be non-differentiable because we don't need anymore to differentiate for that. That said, in the literature, studies about the scalability of biologically plausible algorithms have placed DFA in disadvantage compared to BP. But this is only regarding the test error, so the error on the data set taking consideration. We will see that in the continual learning context, this can be reversed. This was an example on NIST and Cypher 10 of fully connected, and we can see that the error was always larger than BP for the DFA method. The dataset that we will use are the split and the permuted fashion MNIST. We also tested the same things on split and permuted MNIST, and the results are the same. I'm sure most of you will already know this benchmark, but I want to stress that if I apply different similarity measures to the images of the same class among the different tasks, for example, CKA is a measure that is orthogonal invariant. So is one when the two images are only rotated, which is the case of the permuted dataset, and is zero when a rotation doesn't match the two images. CCA is a measure which is linearly invariant, so also allows rescaling. So applying different similarity measure, we can see by eye that the permuted dataset is much more similar among the tasks. Instead, the split dataset has tasks more uncorrelated with each other. We will apply, in this context, DFA with the same feedback metrics and DFA with the different feedback matrices in order to test if the alignment, the implicit bias needs to be the same throughout the tasks, or if what we find is only a matter of chance. We will see that actually learning in different, with the different feedback metrics, so pulling the weights in different direction will be actually beneficial in the most uncorrelated data set. I will show the result with this kind of plot. I will put the backward transfer on the x-axis. So if we are on the higher part, we have zero forgetting, and instead I will put the average test accuracy on x-axis. So if we will be on the right, we will have 100% accuracy, and we want to place ourselves in the right upper corner, where the method will have zero forgetting and 100% accuracy. I'm sure most of you know the definition of these two measures. So our first baseline is a random feature model, because DFA can actually risk to approach a random feature model when the feedback metrics become, the variance of the feedback metrics become very small. We actually find that the variance of the feedback metrics is the parameter that can tune DFA along the plasticity stability trade-off. DFA can reach zero forgetting or can reach 100% accuracy with minus 40 point inaccuracy of forgetting. This depending on the variance of the feedback metrics. As I said before, as the variance is smaller and smaller, B, which is the feedback metrics, will have smaller entries that approach zero. That makes the update rule have a smaller update, because B is directly multiplying the learning rate. So these are the results on the split and task incremental learning. I also put a comparison of BP, which is in the green dots, with two kinds of learning rates, to show that also for backpropagation, the learning rate is the parameter that tune the method along the plasticity stability trade-off. In the permuted dataset instead, DFA has a larger gap to random features. It's more or less 10 point inaccuracy. Instead, before it was only 1 or 2 point inaccuracy. That said, what happens if we change the feedback metrics along the different datasets? So the blue line is the case where the feedback matrix is reinitialized for the beginning of new tasks. So the weights are pulled in different directions. And as I mentioned before, there is only a loss in 5% accuracy and still being able to reach 100% accuracy for DFA with different feedback matrices. So this was surprising at the beginning, but then we actually understood that that of course changing the direction of the bias can be beneficial for uncorrelated datasets. This is also the case of elastic weight consolidation, which is the red dot. These are the results for the task incremental learning, in which the last layer is reinitialized for every new task, and it's specific for every task. But what happens in the domain incremental learning is that where the whole network is shared among the tasks, including the last layer. So below, I show the plot for this scenario. And now the trend is reversed. The FA with the same feedback matrix is more powerful either in the split and in the permuted dataset. And the reason for this is that probably reinitializing the output layer, the gradients needed more time to reach the convergence with the feedback matrix. Instead, keeping the whole network the same and the feedback matrix the same, we can have 100% accuracy. In this case, we cannot reach 0% forgetting, but it's because it's the domain incremental learning. Also in the permuted dataset, in the domain incremental, the performances reach up to -20. The random feature is not anymore available in domain incremental learning because it is based on the fact that the output layer is specific. And in this case, the output layer must be shared. So the summary of my results are that the FA show in the context of continual learning better performance in the backpropagation. We found that the variance of the feedback matrix is the parameter that can fine-tune the FA along the stability plasticity trade-off. And we show that with changing the feedback matrix for different tasks, it can be actually beneficial. For example, in the task incremental learning scenario for the split dataset. Future direction will be, first of all, increasing the size of the network and see if with more and more layers at zero forgetting, we can have larger accuracy. Then, second of all, we are planning to apply the same similarity measure we apply to the datasets to the representations of the network in the intermediate layers. To see, for example, if representations in the DFA same are kept more similar with respect to the representation in DFA diff. A bit of a further direction will be apply DFA to reinforcement learning and continual learning, because there are, for some games, already multi-layer perceptron that work, and we are working with fully connected networks. But in this case, backpropagation is more in difficulty. So we will see how DFA will place in that case. Last but not least, applying and introducing further biologically plausible features. I'm looking forward to hear the dendrite talk at the end of the of the conference, and yeah, we can borrow more biological plausible ideas to the update rule. So thank you very much for your attention, and please, your feedback is welcome either now or this is my email. Okay, thank you very much.
Great, thanks for that great presentation. So now we're going to invite Rudy to present the last paper of this session.
Hello, everyone. It's a pleasure to be here. Okay.
Perfect. Now we can see your screen. Perfect. All yours, Rudy. You are muted, Rudy. Sorry.
Now?
Yes, now.
Okay, just a few words about me, essentially. Rudy Semola, PhD student in computer science at the University of Pisa. My research focuses on the intersection between automated machine learning and continual learning. And this presentation is an instance of my current work on this intersection. In particular, the presentation talks about the problem of using hyperparameter optimization incrementally, effectively, and in a cheaper way for continual learning. In particular, hyperparameter optimization are designed mainly in a static setting, but the real-world scenario is mostly dynamics. The selection of the hyperparameter, most of the time, is doing essentially in a held out validation data from all tasks that is unrealistic, and practical methodology perform HPO for each model update that is expensive. So this is also explain also the difficulty to deploying continual learning to real world application. In this presentation, I want to present essentially and propose a novel methodology in order to perform HPO incrementally with a good performance efficiency trade-off. More formally, the input is a stream of learning task, a configuration space of the hyperparameter, and a continual strategy. The goal is to find jointly optimal parameter and hyperparameter at each task. So the graphical view can explain better this problem statement. Instead of moving only the parameter of a continual learning strategy, particularly the neural network model, given a particular task, we want to jointly move the hyperparameter in order to maximize the performance and, for example, stream accuracy. The desiderata, of course, is optimization without forgetting with a good performance efficiency trade-off. This is we can say, a graphical view of this concept, hyperparameter optimization for continual learning scenario, that is doing by an incremental solution. So on a particular time, we have this training data, and we want to adjust not only the parameter, but also the most important hyperparameter. How? We consider some assumption. So as I said before, instead of using an held out validation data from all the tasks that viola the main assumption of having no access to previous task data, we consider HPO that should be done incrementally. And the first main assumption is instead of fixing the hyperparameter, we consider adaptive hyperparameter. And this way to do improve the performance. The second assumption is in the task in the sequence under consideration. Even if we have different distribution, we hypothesis that we assume that have similar tasks, and this can speed up the incremental HPO. How to select the hyperparameter dynamically in order to speed up the process, so reduce the configuration space. We use FANOVA framework, functional analysis of variance. It's a data-driven approach based on random forest that give a quantitative evaluation of the performance variance caused by a single hyperparameter or a combination of the hyperparameter. It is used, as I said before, mainly in a static setting for minimizing the configuration search space. So essentially, to quantify the importance, we give you as an input the configuration space instance, this random forest, and k, that is an integer that explain essentially if you want to know the single contribution or a combination of the contribution of hyperparameter. Our idea is to assess the importance of hyperparameter across sequence learning tasks using FANOVA framework to automatically select the parameter to be tuned and which could be fixed dynamically in order to speed up the incremental HPO. And this is a graphical view. For each task, we receive the parameter importance by FANOVA. We select the most important automatically in order to speed up the incremental HPO. We also consider considering the second assumption that we have some sort of similarity in the task. If you consider, for example, in the domain incremental learning rotating mist that have essentially similar tasks, we consider to start with the optimal found in the previous task. And this is further improve the computational. And this is the experimental protocol that we are selected. So we conduct the experiment of different benchmark, split CIFAR10, split team ImageNet, core 50 for class incremental learning. For domain incremental learning, we use rotating NIST at core 50 new instance. The strategy are different based on replay category, but also regularization category. And the baseline that we are selected are, instead of using the typical common approach in continual learning, we have decided to use as an upper bound in terms of performance, a lower bound in terms of computational cost, HPO for each model update. The computational cost is very high. The lower bound instead, in terms of performance, but the upper bound in terms of computational cost is performing hyperparameter optimization only in the first experience and keep fixed the configuration for the rest of the sequence learning. We expect to have, of course, an improvement in terms of performance over the in terms of computational cost, but of course we lost in terms of performance. This is a preliminary result. In this particular slide, I show you the hyperparameter importance for learning without forgetting, syntactic intelligence on split CIFAR10 with 5 tasks. This is in particular the overall hyperparameter importance in all the sequence. Note that, for example, for learning without forgetting, learning rate is very important, and for syntactic intelligence is important not only the learning rate, but also the specific hyperparameter, so lambda and EPS, for example. And we use this information in order to reduce the configuration space and speed up the process. This is a preliminary results that start to validate the first assumption that make adaptive parameter improve the performance. The purple is the baseline in terms of essentially keep fixed the hyperparameter in all the sequence. And for example, the yellow part is instead the adaptive incremental approach. In the right part, we have the stream accuracy behavior over the sequence task. In the table, we have the final results with an improvement in terms of performance. In the low part, we are behavior of the learning rate. So it's interesting to note that even if at the beginning select the same learning rate value, decrease for the other task. And this is also could be also normal if you consider that the benchmark is rotating NIST. So we have similar tasks. So and when found the optimal, essentially the suboptimal, remain more or less in the same interval, we can say. Well, so just to wrap up, essentially, hyperparameter optimization is poorly investigated for continual learning, in particular for continual strategy. The common approach is unrealistic, but the practical approach is very expensive. So we propose a novel methodology to perform a realistic incremental hyperparameter optimization with a good performance efficiency trade-off by exploiting the hyperparameter importance information. How? We use FANOVA framework to automatically select the parameter to be tuned and which could be fixed dynamically. That's it. And thank you for your time. If you have any question, please ask.
Great for the presentation. Thanks for the presentation, Rudy. And now I believe that we have time for a few questions. So if any one of the attendees has a question for any of the panelists are all here. So if anyone have a question, please use a Q&A or raise your hand and we will let you unmute yourself to ask the question. So I believe someone from here has a question.
Yeah, hi. Probably Julio. Okay, yeah, you're muted. Fine. Because we are very close, almost. Well, we are in the same room, so I didn't want any echo to sound. I have a question for Sarah and the DFA method, which
Yes, please.
which I really liked. I remember I tried too many years probably ago to work on with that method. I was wondering, in your experience, was it difficult to tune? Like, is this a learning algorithm that runs out of the box? Like, I mean, with backprop, you have hyperparameters like in the optimizer, but you have also now an understanding of how to set those hyperparameters. While every time I work with something which is more bio-inspired, I always struggle with the choice of the hyperparameters, which often are many, right? So I was just wondering, what's your take on it and your practical experience working with it?
Thank you for your question. And no, in my case, I was lucky. I just found on GitHub a package implementing DFA. And the only parameters I can tune are the learning rate, which was very easy to set. It's just one order of magnitude larger than BP, and the feedback matrix variance at the initialization. It is true that biologically plausible algorithm can be hard to make work or to set, but this one was fine. The package is called TinyDFA.
Okay, thanks. No,
yeah.
it's nice to see that the community has advanced and made it easy to work with it. Thanks.
So I don't see any question from the attendees. Maybe I have a question, maybe both for Rudy and for Sharon, given that both talk were kind of a HPO directed presentation. So first, maybe Sharon can answer, but the question is, have you figured out the interpretation of the similarity of the task when changing the hyperparameters in the sequence? For example, I imagine that if a task 1 is very similar to a task 2, the hyperparameters shouldn't move so much. However, on the other hand, if you have a task 1 very similar to a task 2, hyperparameters, I imagine, should change. I don't know if you have seen this situation. Yeah, go ahead, sir.
Sorry. I actually received the similar question from the chat. Our initial experiments showed that the HPO process itself is able to determine the task similarity by, for example, lowering or highering the regularization strength in our case, in our first experiments, if the task is dissimilar or similar. But in our current approach, we are not measuring any task similarity right now. But as I said in the chat, this is very exciting future direction for us to investigate and optimize even better our search space.
Yeah, more or less is the similar answer. Not directly, but by empirically, I noted that essentially, for example, for rotating NIST, it is reasonable and intuitive to understand the similarity. We have effectively a sort of stable hyperparameter value. Instead, if we move, for example, in core 50, I noted in the empirically that this result, the hyperparameter change with different variants. So even if we not measure directly with the method the similarity, empirically I have validated this essentially, the importance of the dissimilarity in the task improve the performance, but also at the same time speed up the HPO, because work around an interval very near. And yeah, anyway, Fanova helped to implicitly to find this, essentially because if an hyperparameter have a great impact, have a great final quantitative value, no, and of course have to change this.
Great, thanks for the answer. I believe we are in time for the break, but if anyone have any question, I believe someone has a question in the Q&A for Rudy. But if any of the attendees has one question, I believe we have time for one question. Going one, going two.
There's one in the chat, I think.
Yes. Okay, maybe I can ask the question for you, Rudy. So first, Rudy, for the presentation, can you explain the HPO method did you use in the examples you showed? And did you try to it for lower SGD learning rate for comparison?
Yes. Okay, I read the answer now. Okay, essentially in the stochastic, in the experiment that I show you, essentially I propose as HPO Bayesian optimizer, and stochastic gradient descent is as optimizer, and yeah, method using the example did you try to lower comparison? And the other, okay. Okay, maybe I don't understand really the answer. Sorry, the question. Sorry.
Maybe we can ask. I believe it was Hamed. If he wants to raise his hand, so we can maybe unmute him.
If I understand the question, the main point was to understand which HPO method. I don't know if there is a name.
Oh, okay.
Of the method. I guess that was the main point, if I understood correctly the question.
Okay, I understand right in this case. Yes, Bayesian optimization in particular, simple Bayesian optimization. And I also explore other solution, but mainly Bayesian optimization with hyperband, for example. That is a variant of Bayesian optimization. Also, other approach, for example, population-based method, but I not find real good results. So my focus is on the Bayesian optimization family methods.
Great, thanks. So with that, we thanks all the panelists today, all the speakers. And with that, we finish the first session of our ContinualAI Unconf, and we will have a quick break, I believe 45 minutes, and we will come back with more keynote speakers talk and hands-on session. So thank you, everyone.